Angular momentum. The way your book explains it, it gives you the equation L is equal to I omega, where L is the angular momentum, I is the moment of inertia, and omega is your angular velocity. I believe you guys will have already been introduced to moment of inertia, yes? No?
No, we are on Friday.
Yes.
Okay. Or Thursday.
So, again, I'm just doing the math right now. We'll get into what it means here in a second. I is given by the mass times the radius squared. The angular velocity is also given by the tangential velocity divided by r. Okay? So, if you start out with this equation, which mathematically, I guess, makes sense starting from here, you can also just substitute these things in for these terms here. So if you were to do substitute I for mr squared and omega for the tangential velocity divided by r, then this r will cancel with one of these two r's, and you'll get L is equal to m times 1r times your tangential velocity. This, in my opinion, is a much more useful equation in terms of understanding it conceptually. But again, we're starting with the math. So with the math, you can use the equation L equals I omega, or you can use the equation L equals m, or the mass times the radius times the tangential velocity. Or there's all sorts of different ways to do it. If you just replace I in this equation, but not omega, you can also get that L is equal to mr squared omega. These two are probably going to be the most useful, definitely for conceptually, sometimes for actually doing the math problems, but in doing math problems, this is useful too. They're all totally equivalent. They all mean exactly the same thing. Mathematically, like, this is all you need to know to be able to solve most any math problem that's given to you on angular momentum. But that kind of sucks. Like, if all you saw was this and you understood nothing else about angular momentum, you could still probably, if you're good enough at translating word problems into math problems, you could ace any test on angular momentum without actually understanding anything about angular momentum. But what does this math actually mean? Conceptually, what is angular momentum? I've got a couple of demonstrations that we can do here. For example, anyone?
Yes.
Yes. So this is a turntable. It just spins.
Yes. No dice, you.
If we can get this going fast enough, you'll see that if he has his arms out wide or his legs out wide, if he's like getting a lot of his mass away from the actual center of mass, he'll rotate really slowly. Whereas if he tucks his arms in, he'll spin a lot faster. If your radius is larger, your motion will be slower. Or if your radius is smaller, your motion will be faster. You guys have seen this in like figure skating and stuff. Why is that? It's because of angular momentum. You can understand it by looking at these two equations here. Angular momentum, just like regular momentum, is always conserved. That's another, we're learning about angular momentum, but we're also learning about conservation of angular momentum. It's another one of those conservations. You have the conservation of energy, you have the conservation of mass, you have conservation of momentum, and you also have conservation of angular momentum. As long as something from outside of the system doesn't come in and provide a torque, angular momentum is always conserved. That is important. So, this is all you technically need to know to be able to ace all the math problems and whatnot, but to understand it conceptually, to understand what this means, if L is remaining the same, your angular momentum is remaining the same, again, your mass is remaining the same as long as nothing's coming into the system. If you increase your radius here, if the radius becomes larger, for L to stay the same, omega is going to have to become smaller, right?
Mm-hmm.
Omega is your angular velocity. Or if your radius goes up, your tangential velocity has to go down. That's what the math means. So I'm going to walk you through the example problem. The average distance from the Earth to the Moon is 3.84 times 10 to the 5 kilometers. Average orbital speed of the Moon when it is at its average distance from the Earth is 3.68 times 10 to the 3rd kilometers per hour. However, in 1912, the average orbital speed was blah, and in 1984 it was smaller. Calculate the distance that corresponds to the 1912 and 1984 orbital speeds respectively. So you've got your average radius, your average velocity, velocity 1, velocity 2, and you're looking for, after I write down what's given, I always like to write down what I'm looking for. You're looking for radius 1, and you're looking for radius 2. But you know that the angular momentum in 1912 has to be equal to the angular momentum in 1984, or the average as well. They give you the averages too. Your average angular momentum is going to be the same as the angular momentum in 1912 and the same as the angular momentum in 1984. So, again, they're just starting from this equation, but what they end up doing, they're just substituting into this equation. So, pretty much, they did the exact same thing that I did here to end up with L is equal to M times R times V tangential. And you know that that's going to be true whether you're doing this for V1 with R1 or V2 with R2 or V average with R average. So you can set those equal to each other. For any of these states, the angular momentum is always going to be equal. So for example, you can say that R1 times V1 times N is equal to R2 times V2 times N. So M's are just going to cancel out of this equation, right? And you could also have set that equal to M times R average times V tangential average, and the M again cancels out. Here, if we want to find R1, we don't know R2, so we're not going to use this equation here. We're going to want to use this equation here. We can use this equation because we know R average, we know V average, and we know V1. Solving for R1 here, we get that R1 is equal to 1. And you just plug these given values into here and solve for R1. Or you can do the exact same thing to solve for R2. Just set R2 equal to this, divide by V2. It's the same equation, only you'll have V tangential 2. And that's how you solve for R1 and R2.